Hello, Professor. Today I want to present the Lecture 11 summary, and today's presenter is Jiajun Jiang. And here is the agenda. First, we're going to start with the different parallelism to show how the parallelism works, and then is the course and stress. And then is introduce some thread CPU and the type of multi-threading, and then is shared memory and messenger passing. And the last is the cache coherence protocols. So first, the different parallelism in applications. The first one is ILP. It is the most basic one. It means multi-instructions from the same program execute at the same time. So we just put the instructions in parallel, like superscalar and VLIW. The second one is task level parallelism. It means several different tasks execute on the same data. Like if we have a data which is a student's age, we want to compute the student's average age and the max age or the minimum age. And the third one is data level parallelism. It means the distributes data across different nodes, which operate on the same data in parallel. And the last one is thread level parallelism. It means the multiprocessor from different programs execute at the same time. Before we start the thread CPU, first I want to introduce what is the cores and the threads. The cores are the physical processing unit. The threads are the smallest sequence program instruction, and it is a component of the process. And the multi-threading allows for better utilization of available system resource by dividing tasks into separate threads and running them in parallel. And the hyper-threading is the further increased performance by allowing processor to execute two threads at the same time. And the first one is single thread CPU. We can see the picture. In this picture, each color represents a running program, and the white space represents the pipeline bubbles. So we can see the picture. We can see there's a lot of white space in the front end in the CPU. In this case, the processor can issue up to 3 instructions per circle, but it is very hard to reach it. So the single threading can only allow the CPU process one color in one time. So there's another type. It is still the single threading, so the CPU can just accept only one color, but this time it will have the multiprocessor. So the system can schedule 2 independent processes on each core. But the problem for the single threading is not fixed, because there are still a lot of empty slots in the CPU. So the third type is single core multi-threading. It also called super-threading. The processor can execute instructions from multi-threading. So we can see the picture, the CPU are already accept there's a 2 color in the CPU. But there's another limit, is the processor pipeline stage can only accept for 1 thread. So on each row there's only 1 color. The last one is called simultaneous multi-threading. It also called hyper-threading. The main difference between the simultaneous multi-threading and the multi-threading is the simultaneous multi-threading don't have to limit by the pipeline stage, only can contain 1 thread. So we can see the picture, the different pipeline stage, it contains different colors in the CPU. And then is the type of multi-threading. We are already discussed about the multiprocessor and the simultaneous multi-threading. But there are 2 more for the multi-threading. There are fine-grained multi-threading and the coarse-grained multi-threading. And the reason why we want to use the multi-threading is to let the OS can have better resource utilization. So when the thread is stalled, we can switch to another thread, so we don't have leave a lot of white slots in the CPU. So the fine multi-threading, it is very simple. First, we can see the picture. There's 5 different colors. And we know the basic pipeline stage. There's 5 steps. The first one is fetch, decode, execute, memory, and write back. So the 5 different color, we can guarantee there's no dependence between the instruction because you have to wait for the whole circle till the next stage. So the advantage for the fine multithreading is no need for dependency checking between the instruction because we can make sure there's no dependency, and no need for branch prediction logic, and it can improve system throughput and utilization because if we have no prediction means we don't have to stall the CPU. But the disadvantages are also very significant, like extra hardware complexity and reduced single thread performance, and the dependency logic between the threads are still remain. And then is the coarse grain multi-threading. The main idea for the coarse grain multi-threading is when a thread is stalled due to some event like the cache miss or the page fault. If the processor encounters low store, we have to switch to different hardware contents, so make sure the CPU is still running. This method looks good, and the advantage for the fine grain is it is simpler to implement and easy to emulate the dependence checking and the branch prediction. If the instruction is stalled, just switch to another. But the disadvantage for the coarse grain multi-threading, it will have a very low performance in the single thread. So the simultaneous multi-threading, it combines the advantage of the ILB and the fine multi-threading. It allows the thread to execute out of order and get better utilization. And then is the limitation of the speed up. There are 3 main reasons to limit the speed up. The first one is inter-processor communication. It means when a processor is compute a value and it is needed by another program running on another processor, so you have to communicate the data between one processor and another one. And the synchronization is we often need to synchronize processor to ensure that they have all complete the same phrase before continuing. And the load balancing it is very difficult to divide the program across processor such that each processor has the same workload. And we are gonna discuss the inter-processor communication. And there are 2 major programming models for the multiprocessor system. The first one is message passing. The second one is shared memory. The characteristic for the shared memory is the shared memory processor can provide all the processor a single address space, and it allows any processor can read or write the data in the memory at any location. And no matter read or write from any processor, the timing is the same. We call those machines are uniform memory access multiprocessor. Otherwise, we call those machines are non-uniform memory access multiprocessor. And then is the messaging passing. In messaging passing multiprocessor, each processor has its own private address space. The processor shares data by sending and receiving information. And the processor cannot read or write data contained in another process address and space because they just can read it and write on their own address space. And then is memory consistency models. There are 3 different type of consistency model, but today we only discuss the strong consistency and relaxed consistency. The strong consistency means all parallel operation must guarantee the same result if execute on a system with a single memory system shared all the processor. And the relaxed consistency allows read and write to complete out of order, but the operation it have to be ordering. So the advantage for the strong consistency is it is simple, but the disadvantage is the performance penalty. And the pros for the relaxed consistency, it can have the better performance than the strong consistency, but it is also required complex in the describing models. And then is cache coherence protocols. The cache coherence protocol of shared memory system is to describe how the data may be shared and replicated across the processor. And there's two protocols. The first one is snooping protocols. We can see the picture. We just add a snoop tag beside the cache, so the processor snoop the bus to see if any data in their cache has been updated. And the directory-based protocol is to keep track of what is being shared in the centralized location. It is very commonly used on described memory machines. And then is the NSI protocols. The N represents the modifier. It means the block has been modified in the cache. And the S letter represents the shared. It means this block is unmodified and exists in read-only state in at least one cache. And the I represents invalid. It means the processor has no copy of a line. So we can see the picture. We can see there's a problem because if on a read, the blocks will immediately goes to shared state, although theirs might be the only copy to be cached. The problem for the NSI protocol is that by default all data is loaded in the shared state, even if there is no shared. When we move the cache block X from the shared to the modified state, we must send out a signal to the other cache to invalidate their copies of block X. If they don't have a copy of the block X, then we will waste the bus circles. So to prevent this situation, there's another pipe. It's called messy protocol. The difference between NSI and NESI is the extra state exclusive. The exclusive means the processor is the only one with a copy of the line and it has not written the line since. And the right picture is to show the state transition in NESI protocol. And this is all I have for today. Thank you, Professor.